Hello and welcome to Technology and Space, where we talk about the science, technology, history, and business of space exploration and commercialization. I'm Chris Alvarez, and thank you for listening. This interview will be presented in two parts. This is part 2.
See, here's the way it would work. Before the mission starts, the scientists propose experiments. So there's about a big science team, maybe about 15 or 20 people, and they all have and in order to get on the science team, you submit a proposal to NASA, and then NASA, you tell them how much money it's going to cost, maybe $1 million or something like that, and then they approve it, and then you become an investigator, and then a principal scientist is the principal investigator. Well, I'm the principal navigator. Of course, nobody would recognize that position, but I did. So I had to get gravity fields and planetary ephemerides and all that kind of stuff. And since I didn't have a NASA grant to do it, in theory, I'm not allowed to do it then, because I'm not allowed to do science because I'm doing navigation.
Got it. Okay.
It's like, look, most of your science, a lot of your science that you're doing is navigation, and I've already done that science. So I'm going to use my science unless you can convince me that your science is better than my science. And if you don't like it, that's too bad. And I told the scientists a couple of times, I said, if you go off and do something with your own software, and Goddard had software that would do a lot of this stuff, but they didn't have the optical tracking. So I told them, I said, if you have any problems, I said, I'm not going to help you. But if you use my data that I'm providing, which is the official project data, then if you have a problem, I'm going to make sure that I get it fixed. So that was the deal that I worked with them. Well, of course, they didn't like that because first of all, I don't have the authority to tell them anything like that. But after a while, they realized that I had a hell of a lot more authority than a lot of people. Because when I told them something, they usually started doing it.
So let me ask you about gravitational fields to better understand them. So is the gravitational field sort of a sphere around the center of gravity, or does it fluctuate? Like what's sort of what would you say is the shape of gravitational fields?
Okay, well, what happens is I'm working on a paper or a book on general relativity right now. And one of the things that, like the gravity field, if the sun, let's say, for example, this is the assumption that's made, is a perfect sphere in uniform density, then the external gravity field is very simple. It's just 1 over r squared. In other words, you just take the inverse square of the distance from it, and that's the acceleration. That's your gravity field. Okay. And that's an extremely simple gravity field. Well, with general relativity, it gets a little more complicated because you have to add in a little term, 1 mu over c squared r cubed. There's an r cube in there now. Okay. But it's such a small term that it doesn't make much difference. Well, when you're talking about the Earth, there's enough irregularity in the shape of the Earth that you can't assume it's a perfect sphere. Okay. So mathematicians back in the 1800s, my heroes, these are the guys I really like. I kind of wish that I could just go back and talk to these guys and tell them what I've done and how much I appreciate the work that they've done. Because these are the heroes of science, really, in mathematics. They came up with Legendre polynomials, they call them, and it's a way of accounting for the irregularities in the shape. Okay, so the big one on the Earth is that the poles are about 4 kilometers away, shorter in one direction than the other. The equator is about 4 kilometers in radius, bigger than the pole, the distance. It's squashed, in other words, and it's in that ellipsoidal shape because of the rotation. See, the rotation throws the mass, stretches the Earth in the equator direction, and flattens it in the pole. See. Well, not only that, but there are mountains on the Earth. So a mountain has gravity. So actually, if you're standing in Nebraska and the Rocky Mountains are over there to the west, you're not standing straight up. You're actually leaning a little bit toward the Rocky Mountains. You can't measure it. You can measure it, but it's really small. Yeah. Well, you walk around on the surface of the Earth, if you have a plumb bob, it should point right straight down to the center of mass, but it doesn't. It's always, they call it the deflection of the vertical. Mm-hmm. And this deflection of the vertical is, for intercontinental ballistic missiles, is critical. Because when you launch the spacecraft, you have to compute the gravity. The gravity isn't something, and you can't measure gravity with instruments, with inertial instruments. You have to compute it. So that's the same thing true, with this asteroid. But now the gravity field has huge harmonics, way outside of the linear range. So the little bumps on the asteroid caused deflections of the gravity. Well, it's big enough to affect the motion of the spacecraft. We can see it. So one way of solving this is what's called gravity harmonics. You come up with a mathematical set of harmonics that are sines and cosine functions that are kind of difficult to derive, and the Legendre polynomials that take care of the gravity along the axis, and you solve for these coefficients, and then you can compute the gravity, and the gravity vector, the direction and the magnitude of the gravity, is a function of all these harmonic coefficients. Mm-hmm. But for a sphere, it would point straight to the center of mass, and that's 90%, or that's a 99.75% for the Earth, or more than that. Well, like for example, okay, I'll tell you another little story.
Sure.
This is interesting. When we flew by the Earth on Galileo, it was, and a couple other missions before that, most of your trajectories are Earth orbiters are in the equatorial plane of the Earth. Mm-hmm. It's hard to get over the North Pole unless you launch it that way. Like in Vandenberg, they launch over the North Pole. Mm-hmm. But on Galileo and even on Near, it was really dramatic. With the spacecraft, it has to fly by the Earth to get a gravity assist. So when it flies by about 900 kilometers away from altitude or so, mm-hmm. and the gravitation of the Earth gives it a slingshot effect. It throws it out to where you want to go.
Right.
Okay. Well, when you fly over the north, we fly over Siberia and then come down over Antarctica. What we noticed was that when we solved for the velocity of the spacecraft, it was off by about 1 or 2 millimeters per second. Now you think that 1 or 2 millimeters per second, that's like the second hand on a watch. That's not very fast. Mm-hmm. It's a lot. You can walk a lot faster than that, but it's a lot in an orbit determination situation. Mm-hmm. Because if you propagate it out for a year or so, you could be thousands of kilometers off if you're off by a millimeter per second.
Right.
But we noticed this, and we figured there was something wrong with the gravity field. At least that was my theory. It was an unexplained phenomenon. Well, the scientists that are associated with the astrodynamics part of it, they never have anything to do, because we know how the gravity field works, and we don't really need them. So if there's something that's unexplained, this is their day, they managed to keep this unexplained phenomenon going on for years. But they asked me, and I say I know what the answer is. It's the gravity harmonics are wrong. Well, they have University of Texas, I guess, is doing these gravity harmonics, and they have them out to like 10,000 harmonic coefficients. And I said, that's not enough. I said, here's what you have to do. Consider Iceland. Iceland is sitting there, right? If you took Iceland and moved it to the middle of the Pacific Ocean, that would explain the 2 millimeters per second. Mm-hmm. And since you don't have a gravity field that's accurate enough to recognize the Grand Canyon, let alone Iceland, the gravity harmonic coefficients are not accurate enough to actually recognize mountains and topographic features on the Earth. Now,
I see.
Nowadays, they can see some of it. I'm not sure where they are right now, but I'm talking about 20 years ago. I don't know what they have right now.
Okay.
On an asteroid, we could get the shape. The way I got the gravity field on Near was they had one of the science instruments was a laser altimeter. So as the spacecraft orbited around in a polar orbit, it covered the whole body. They fired this laser beam down. It would hit the surface and bounce back, and then they would detect the return, and they measure the round trip light time, and that tells them how far they were from that point on the surface aimed at. So I said, gee, I could use that for navigation, because then I can determine, I know where the center of gravity is, so I can subtract off, and I know where the spacecraft is, so I could subtract and get the radius to the surface. See, I could figure the shape of the thing. I can get the shape of the asteroid by using these laser altimeter measurements. Well, the principal scientist for the laser altimeter experiment was from Goddard, and very uncooperative, figuring that since navigation doesn't have anything to do, because it's well known how we navigate for the last 20 years, and you're not really doing anything new, I don't have to pay any attention to you. And I kept saying, I need this data. Well, usually, and so I get no cooperation from science, because I don't have a science contract. But I was on the science team, by the way. I was on three of the science teams. After NEAR, they won't put me on any, because they didn't like the way I behaved when I was on the science team. They thought they could buy me off by putting me on the science team. It didn't work at all.
Backfired.
It backfired, right.
I'm speaking with James Miller, author of Planetary Spacecraft Navigation. You can find more information about his work at the Springer website. If you like this podcast, Technology in Space, so far, please subscribe to it and rate it if you can. If you want more science, technology, and space history, please visit technologyinspace.com to sign up for my weekly newsletter and keep track of my latest posts. You can also find written interviews and my social media links there. You can find the links to my other podcasts at militaryhistorypodcast.com and fullcontactnerd.com. Now back to the podcast. So you're saying, so he didn't want to give you the laser data, altimeter data?
Yeah. Okay. So now we get into orbit, and I got this gravity field, and I didn't know whether it was any good or not. All right. And so I'll tell you this story, because this is one of my favorite stories to tell. There's a woman back at APL. Her name is Yanping Gao. I'll mention her name because I know her very well. I got her to give me a recommendation for the book. She was one of the people. So she was treated very badly, of course, because there's a lot of politics that goes on in any organization, and the sciences, the engineers did not like the scientists, same as JPL. Right? But I'm the only engineer that doesn't like the scientists. The rest of them don't even know what's going on, so they like the scientists. But the politics is really severe. So she was aware of the fact that I wanted to get this laser altimetry data and understood why. So right in March, I guess it was, of 2000. She sends me 100,000 laser altimeter points in a file, which I had kind of got. I said I wanted this file, and I kept reminding them that the MCO spacecraft was lost, and the reason it was lost was because the file that determined the non-gravitational little accelerations on the spacecraft, they never provided it. And you guys, I've asked for that same file, for you to generate that same file, and you haven't provided it because you decided that you don't need it. Well, when your spacecraft crashes, I'm going to remind you that you didn't give me the file I asked for. So she listened to that, and she realized that this other file was another one that I was asking for. So she provided it, and I took it, and I had some software written, and I had a guy that was working with me that I turned it all over to him. But I, for this particular one, I decided to jump right in, and get that data and process it. So what I did is I determined a shape model for Eros, strictly from the LiDAR data by itself. I had a solution for the gravity field that was radiometric. In other words, it involved tracking the spacecraft and then measuring the acceleration of the spacecraft. I can determine the harmonics of Eros. But if I knew the exact shape of it, and I made the assumption that the density was constant, there's no mass concentrations buried in Eros. It's all the same mass, all everywhere.
Okay.
I had the mathematics that I picked up out of books that I've read and derived myself. And really, this was not easy to do, but I did it. I could integrate over the shape of Eros and determine the gravity coefficients. So I did it, and I looked at it, and then I looked at the solution, the radiometric solution, and they were so close. I immediately came to the conclusion that I'd made a mistake. I got the fields mixed up. So I spent an hour doing it over and over again because I couldn't believe that the solution I got from the shape was exactly the same practically. Out to the fifth degree in order. This is like 500 or 600 coefficients. They're all the same. I thought, this is amazing. I said, this proves that Eros is constant density. Or the scientists always have some phraseology or words that they make up that completely confuse everybody else. Constant density means something to me. It's undifferentiated, is what they would say. That means there's no differences in the mass. It's undifferentiated. That was a big scientific discovery. So I first thing I did, we had a guy that was on a science team, but he was on the radio science team, and he was doing gravity modeling. So I walked over and I said, "How's your gravity modeling doing?" He said, "Oh yeah." I said, "Pretty good." I said, "Can I see your gravity field?" So he got it out and he showed it to me, and I looked at a couple of the coefficients, and then I looked at mine. I said, "That's wrong." I said, "You're wrong." I was kind of teasing him, and he says, "Well, how do you know?" Essentially, I told him what I did, and I said, "Here's the correct solution. I got two of them. They're doing the same thing, and yours is different from these two." So he said, "Oh," he says, "I know what it is." He said, "Can you tell me where the pole is?" See, the pole is the direction of the spin vector of Eros. That's something I had to solve for. So my solution was about 4 or 5 degrees off from where they thought it was before we started. That's a huge amount. So he probably knew it within a degree or so, but he needed it to be within 1/100th of a degree. And so I gave him the pole, and then he reran his software, and then he got the same exact result as me. So my policy is that when I make a great discovery that I should be awarded the Nobel Prize for, I immediately just forget about it, because his job is to determine the gravity field, and I don't want to embarrass him because he's a friend, and I have to work with him in the future. So I just never said another word about it. I just went on. Okay, now in the meantime, I'm fighting with this person at Goddard, who is famous, who was on the team that investigated the Challenger explosion with Feynman. One of those shuttle explosions, and who was very hard to get along with. And I'm in competition. I'm not in competition. I'm doing the navigation, and you're not doing the navigation. That's my attitude. So I decided that she's not going to know. It was a woman too. She's not going to know. Her solution for the gravity field is probably not going to be is going to be like the other guys. She's not going to know what I know about. So I decided I could be quiet, even though she's an enemy, and just let her spin for herself. So I called her up, and I said, "Look," I said, "I just discovered that the gravity field that Eros is undifferentiated, as they like to say, and what I had done." And I said, "I'll tell you what I'll do." I said, if you want us to write a paper together, I'll just give you what I got, and you can write it, and then you could put me on the paper, and that'll be all I want. That'll be fine. I'm not gonna publish what I have as a finding. I'm just going to give it up." And she said, "Well, that would be unethical. You're unethical." I said, "What?" I said, "Of course, I'm an engineer. You think I'm ethical?" I said, "Look, I know you know the director of this laboratory. I said, and you could call him up and probably complain about me giving you trouble. I said, go ahead and do it, because I don't pay attention to him either. So after that, I never had any problems with her anymore. Mm-hmm. And she did her stuff and I did mine, and that was the end of that.
Mm-hmm. And the paper got published?
Well, as it turned out, she publishes in science journals, and she didn't want me to publish in a science journal. I have to publish in an engineering journal. Well, engineering journals are not respected by scientists. So I said, no. I said, look, if I do something that's, so I agreed not to publish this thing at all, period. Mm-hmm. If I'm going to publish it, it's going to be in a science journal. Well, when the mission was over with, this is a year or two later now after this conversation, I don't think I talked to her again after that. I still haven't talked to her. If I ever saw her again, I would be friendly with her. Mm-hmm. Anyhow, we wanted to come up with a paper for Icarus, which is like the most prestigious journal for science, for space science.
Okay.
It's Cornell. I think Carl Sagan had something. He was editor of Icarus, and Joe Vaverka was now and I knew Joe, but it's like Science Magazine. A lot of the stuff I did went into Science Magazine, not under my name. I was named as one of the many authors, which really made me mad because it was mostly my work. But anyhow, I decided that 90% of the work that was navigation, not radio science, and I had done it. So I am going to write the paper for Icarus. If I'm not the lead author on the paper, I'm not going to contribute to it because it's my work. Mm-hmm. And I could have pointed out to him that what you're engaged in is scientific fraud, and I'm going to call up the FBI and have you investigated. I didn't say that, but I thought it. But they probably thought it too, and so they let me be the lead author on this paper that went into Icarus. Mm-hmm. So I wrote the paper, and of course I got all my experts that are on the team, to help me. Mm-hmm. And sections of it. I didn't write the whole thing. But it was a really nice paper, about 15 or 20 pages, and it went into Icarus. So I sent in my draft, and the scientist then sent back comments on it. So the comments was one comment was, I regarded this one as really a very positive comment but I'm sure he was making it as a very negative comment. Mm-hmm. He said it was the description of how you solve for these 600 parameters is impossible. It's impossible to do what you did. I thought to myself, God, I did something impossible. But his thought was that you don't know what you're doing.
Yeah.
So I just disregarded him, And then somebody wrote down and says, there are a lot of people on this paper who have great reputations that work at JPL. This paper is going to ruin their reputations. They're going to, because this paper is so bad. So I wrote a letter. I wrote a quick letter to the editor, and I said, whoever that was has no business talking about how JPL does their business, because I've been working with these guys for years, and we all know where we stand. I said I'm not paying attention. And then I answered the technical points one by one. I said, here, I don't understand. Here, this is what's going on. I wrote, it was a 2-page memo. Mm-hmm. And then I let it go at that, and I submitted I reviewed the galley proofs and submitted it and forgot about it. Mm-hmm. Well, they had a special issue of Icarus that came out. My paper was the first paper, and it was the only one that discussed a lot of the issues that were very important.
What year did that come out? That issue?
2003, I think.
Okay.
Around 2000. No, wait, 2001. 2001, 2002, somewhere around there.
Okay.
And that made my career, because on Icarus, that paper has received 900 downloads. 900 different people have downloaded it. If anybody does anything at all with asteroids navigation, they get that paper. That paper is the defining paper for navigation around asteroids.
Cool. Just so I don't forget, the meeting you mentioned where JPL and APL were trying to refight over who had the program. What year was that meeting? Do you recall the one you talked about?
I do recall 1993.
93. Okay. Just trying to get my timeline straight there.
Well, yeah, that was when because the earthquake was in 1994 here in California, and I remember right after I started working on it, we had the earthquake, because I was in Baltimore, I think, when the earthquake happened. No, I was here when the earthquake happened, but they knew about it. Yeah. Okay.
Okay. So you mentioned in your email sort of there was a point where the spacecraft had a flat line that you were like in dread of something going on. Do you want to?
Oh, that one. Okay. That was the one exciting part. One of the things when I'm bragging, I brag that I've never worked on a mission that failed. Mm-hmm. Mission that I worked on was more or less 100% successful, unless I quit, or stopped working on it. Then it was possible to have a failure, because I wasn't there to make sure it didn't happen. I always embellish this a little bit. but anyhow, we're going to insert into orbit around Eros. So the deal was that my supervisor and most of the guys are going to do all the interplanetary navigation, because I'm not interested in interplanetary navigation. Mm-hmm. And the orbital phase is where the real work was going to be done anyway. I did do. One of the guys quit, and so I took over for a couple of weeks or a month or so, the flyby of the Earth, where that little 2 millimeter per second would happen. Mm-hmm. So I was actually the navigator on that. But anyhow, interplanetary navigation, I wasn't doing it. So they had a plan where, as they approach Eros to rendezvous with it, they're going to do 3 burns. So they burn an engine for, and reduce. There's 900 meters per second velocity difference. So you have to take out 900 meters per second. So they took out maybe 600 in the first burn, and 40 in the next burn, and 10 in the next burn, and then they're in orbit. So we're sitting there, and I'm actually sitting in operations now, at JPL. And my policy is that if they're doing something that I disagree with, if they won't do it the way I know is the correct way to do it, I won't show up for operations. I'll just go down to my office and sit there, and then when they screw up, I'm going to come up and blame them for everything. Listening to them. So I threaten them. But anyhow, I'm sitting there, and I'm engaged now, because I'm on the team, and I'm not fighting anybody. And when you look at the Doppler data that comes down from the spacecraft, it kind of looks like a heart monitor. There's little points, and they get plotted in real time. Mm-hmm. So you can see the little points going along, and they're jumping up and down. It's like a little cloud around the zero line of points. Each one of these points is probably $500.
Right.
Anyhow, so I'm sitting there looking at it, and all of a sudden, the line goes to zero. It's like when you see an earthquake. It's much like an earthquake. Mm-hmm. You see a little earthquake, and then the line is flat. Mm-hmm. So it flatlined. So being a experienced, trained navigator, I immediately started to blame the DSN for screwing up the computers, because that's 90% of the time that's the problem. Mm. When it wasn't, what happened was, when they fired the engine, it went out of control, and the spacecraft started tumbling.
Oh wow!
And it burned up about 50 meters per second of propellant, and threw propellant, the byproducts, sprayed it all over the spacecraft.
Oh wow!
The gooey stuff, that comes out of there. And the reason was that the guy who was at APL that was responsible, he got the wrong coefficients, I guess, in the control. So this is he was one of supposed to be the smartest guy on a near team from APL, and he turned out he made a big mistake. Mm-hmm. So the spacecraft flew by Eros. It didn't slow down. It just kept on going at 900 meters per second.
I'm speaking with James Miller, author of Planetary Spacecraft Navigation. You can find more information about his work at the Springer website. If you like this podcast, Technology in Space, so far, please subscribe to it and rate it if you can. If you want more science, technology, and space history, please visit technologyinspace.com to sign up for my weekly newsletter and keep track of my latest posts. You can also find written interviews and my social media links there. You can find the links to my other podcasts at militaryhistorypodcast.com and fullcontactnerd.com. Now back to the podcast.
Now, so we immediately, they analyzed it and they determined what it was. And we had a big meeting. There was like hundreds of people on the phone, because anytime anything happens, there's a lot of people who want to come around to see what's going on. You know, they're never around beforehand to help you out. and it was determined that what had happened. So the guy knew how to fix it. So the fix was to turn the spacecraft and burn to stop it, and then have it come back at a very slow rate. You don't want to burn any more propellant than you have, so that so if it flies by for a day, it takes a week to get back.
Okay.
So I said, okay, well, what we do is do that burn right away, you know, and all that. And they said, no, we've got to think about it. We've got to make sure, we got to absolutely be sure. So I said, look, you can check all you want. You're not going to get any more sure than you are right now. Just do the burn, and if it blows up or anything else happens, that's too bad. That's the end of the mission. No, they don't want to do it. So they let it go for 10 days. So now when they do it, it's going to take a year to get back. So that all the money for the extended mission is gone now. That was extended mission money. So they stopped it, and then slowly brought it back. Well, this enabled me to do some stuff that I found kind of really interesting. I got a really good images of the asteroid as it flew by, you know, and all that, from a different angle, and then coming back, you know. So I was able to essentially determine where the asteroid was relative to the sun, the very high precision. I knew exactly. Yeah, I don't even need to know it, because once you get there, you don't really care where the sun is. But anyhow, that happened. Yeah, there was one other thing I was thinking of that had to do with the same sort of. I know. This is where my experience came in once again. We decided to land on the asteroid. I didn't decide. I was against it. So my attitude was, all right, I'm not supporting it. So they never asked me to help them. They just decided that they're going to do it. And I hadn't been working on the operations very much at the end there. I was doing something else. So they did it, and then I looked at what they did. I said, tell me your maneuvers, and I analyzed it, and I determined that this landing was going to be successful, unless the spacecraft fails. This is a good idea. The only way, in other words, we could do maneuvers down to 1 millimeter per second, and as long as you get down in 40 minutes, you're going to get within a 100 meter circle. So I'm pretty confident that it's going to work. So we're doing it, and the thing's coming down, 20 minutes, 30, and I thought ahead a little bit, and I said, how are they going to know that it's safely landed? Well, my supervisor had figured out that if you look at it with the Doppler, the rotation of the asteroid around its axis is going to cause a Doppler shift. And you can compute that. It was like 14 hertz, we call it. That's the Doppler shift. So when it lands, we're going to see a 14 hertz Doppler shift. Well, I knew that is a positive indication that's safely landing. But it's just one little indicator. So everybody else I knew is going to be unsure about the landing, because they're going to think that, we see the 14 hertz, but does that mean it really landed? There's no way you can get 14 hertz other than being on the surface at a certain point and have it go. So I knew that they were going to stand around and not do anything like they normally do when something unusual happens. And we were on a internet on a phone connected to APL in Baltimore, and I'm in Pasadena, and we watch it, and it lands. A guy announced, "Okay, it should have landed right now," and I look at it, and bingo, the thing goes to 14 hertz, and start tracing a line across at 14 hertz. So I knew that they would not know whether or not it was landed. So I got on the phone and I said, "Okay, you guys can now start to celebrate because it's on the surface and it's landed." and about 5, what I didn't realize is that since they knew I could be on the line, that my statement didn't go to the whole world like it had in other times in the past. So about 2 minutes later, there's a big cheer. All of a sudden, it's landed. I'll tell you one other story like that. When they had this blow up or the engine failure, we lost 50 meters per second. We had 75 meters per second to do the whole mission, the orbiting mission, because they always put more on than they need, which is all right. What we really want to do is do an extended mission with what's left over. But so now there's only 25 meters per second left because it burned up to 50, and they coded some of the optics on some of the instruments too. Couldn't get as good pictures. But anyhow, the question is what are we going to do? Well, I had designed the orbiting mission. Now, of course, nobody recognizes that everybody's talking about how to design it, and I'm not listening to anything they say. And then when they decided to design the mission, this is about 3 or 4 months earlier. It's pretty late for designing an orbiting mission. I said, okay, well, since they think they know so much about designing the mission, I said, let them design and come up with a design, and then we'll see how it goes. And my supervisor calls me into his bosses, and they got a notepad there, and they're getting ready to fire me because I designed the mission. so I'm talking to them, and I said, okay, I listened to everything you had to say. I said, I'll design the mission, okay? So I designed it, and it took me 2 days to design it because I knew I had designed missions like that on Viking, and a lot of times I knew how to do orbit elements and all that kind of stuff. So I knew I could do this really rapidly. It wasn't easy though. Let me put it that way. So when the disaster occurred, they said they wanted to know what can we do with 25 meters per second. So I got on a telecon, and there were like 300 people wanting to know what's going to happen on there. So this time I'm actually on the line with it so that everybody can hear me. So I said, okay. So I got really serious. Normally, when I'm making outrageous, stupid statements, I know who's in the other room, and I can just say whatever I want because I know they know me. When there's a lot of people who I'd ever heard of, and there's NASA people and all that on the line, I don't want to say anything that's going to screw things up.
Right.
So I said, okay, here's what you got to do. I said, when our plan was that when we get there, a couple of weeks later, we send the spacecraft into a polar orbit and fly over essentially the subsolar point. In other words, we're going to fly such that the spacecraft is exactly between the asteroid and the sun, so that you can look straight down and you can see the sunlight is right behind you. See? And the infrared spectrometer guy, Jim Bell, he wanted that data, because he wanted it early. And I said, look, what we can do is not do that overflight there, but wait about 2 or 3 months. And when we get into the situation where we have to change the direction of the orbit, because as we go around the sun, eventually we get into a situation where we're going around in a like a clockwise direction around Eros, and then because the spin vector is fixed in space, when you get on the other side, it's like winter is in. When we're having summer, the South Pole's having winter. When winter comes, we have to turn it around so that we got summer. Let me say it that way.
Okay.
So when we turn it around, we're going to have to fly over that point. So that's a good time to do the experiment. And if you do that, we'll save enough propellant such that we can do the whole mission for 25 meters per second. And the project manager, who normally doesn't like to hear me say anything, he just kind of sat there and he said, okay, go ahead and design that.
He liked it.
Like that. And that was the end of the telecom.
Interesting.
So I sat down with, and I didn't actually design it. I got one of the guys that was young and ambitious and all that. And I knew he's going to have a good future. So I got him to design it and I helped him.
When the Near landed, how do you know it didn't crash rather than land? How did you know it was a safe touchdown? Because
the transmitter was working.
Oh, okay.
See, if it crashed, the transmitter wouldn't be on. And not only that, but it has to transmit from a low gain antenna because there's a dish on there. You can't point. The dish would not be pointed at Earth.
Okay.
It's very hard to get the signal, and they couldn't get any data from the surface. We got a good data going down, right to the few meters above the surface. We could see the pebbles and everything, and then bingo, that's the end. It landed. So the only indication was the return of the signal, and the only information we had was the frequency of that signal. So from the frequency, we could figure out the Doppler shift.
Okay.
And then that told us that we were where we thought we were, and we had landed.
Okay. So you mentioned being worried about this current mission that's landing. Can you go into any detail about why you're concerned, or?
Well,
you don't have to if you don't want to.
I can make a general statement. Okay. I don't want to say anything. When the Rosetta mission was going on, I talked to the guy before, about 2 months before they did try the landing on Rosetta, and he was discussing about things that he was doing, and there was a group of about 10 of us, 5 or 6, and Yang Ping was there too, and she's a responsible manager at APL. I told him, I said, look, don't pay any attention to those managers. I said, what you have to do is get that damn spacecraft on the ground. That's the only thing, and you need to get a good gravity field to do that. And after it crashed and it landed on its side, I saw him again at the next conference, and I looked at him and I said, the problem was you didn't have good enough instrumentation on that spacecraft. They spent $1 billion for it. For an extra $1 million, they could have put the adequate instrumentation on there, and it would have landed. But because they didn't understand it. And he said, I know, we discussed that. I said, okay. Well, I've made a few statements about OSIRIS-REX that I'll remind them depending on how it happens. If it's successful, I'll congratulate them and it will be a good accomplishment, because what I did is when I retired, I sort of said to myself, I'm going to stay in the game until somebody does something landing on an asteroid that shows that they know more than I knew. If there's been some progress, if they can equal me or less, then I'll keep working. And so I'm still working, waiting for somebody to have a successful landing on an asteroid.
Okay.
So the problem I see is that the problem that with all of the organizations that are doing this, the kind of software that I wrote is very expensive to write, especially if you have a team of people and you just don't have one guy writing it and hoping for the best. So it costs a lot of money to develop the software and it takes a lot of engineering time to do studies to make sure that it's going to work. But the money for the studies usually comes through. You don't have to worry about that. But the software has to have the capability to model correctly and in great detail. And one of the things that's very important is modeling the data. It's hard to model data, especially image. I actually wrote programs to generate images for NEAR. I generate images of craters with asteroids on them and with craters on them, and then I would run it through the software, process the craters, and determine the inertia tensor and the physical sizes and things of the asteroid. the weight, the mass, and all that.
Mm-hmm.
I was able to simulate very accurately exactly what we're going to do in operations. What they do is and then when we got there, I throw away all the simulation software. It's in a certain, because I'm not interested in studying what's going to happen anymore. It's happening right now.
Right.
The it's happening right now software isn't always as good or is adequate to do the job. But the study software that I throw away has never been written, and it hasn't been done. Okay. And therefore, you're setting yourself up because you haven't looked at all the possibilities and planned for them. You're setting yourself up for disaster. But they think that since it costs so much money to do all these studies, that it's cheaper to not do them.
Yeah, just depend on what you did before, the planning.
Yeah, well, I remember on Viking, we're spending over $1 billion for this thing, for 2 spacecraft. And a couple million is nothing compared to $1 billion. Mm-hmm. But a couple million here, a couple million there, and the next thing you know, you're talking real money. Mm-hmm. And that's the way they're thinking, see? Yeah. But you never want to shortchange yourself on navigation.
No.
And they do. Because everybody's cutting costs. Well, the spacecraft, when I worked on Mariner 6, I used to tell my supervisor, I said, look, they're spending all that money and time designing that spacecraft. It's going to cost $80 million. Well, that would be like 300 million today. Mm-hmm. $80 million spacecraft. And it was gold plated. I saw it before it went up there. Boy, I'll tell you, few things I've ever seen in my life that was more impressive than looking at that spacecraft. Talk about money, boy. It's like looking at the crown jewels. I'd rather have that spacecraft and the amount of money that you're spending, you just have to on Viking we spend it, in other words. Mm-hmm. We spent so much money on navigation, but still it only amounted to maybe a few million dollars. Well, maybe 5 or 6, not counting the data. Mm-hmm. This is interesting. You're taking all this expensive data from these DSN stations, which cost millions of dollars. Mm-hmm. That's on one, but the navigation is the sum of that, plus what we do navigating, the computer part, where we write the computer programs. But for every little data point that we're processing, there's enormous antennas. There are 200. If you put them in a Rose Bowl, the antenna would go from the goal line out to the opponent's 40-yard line. Mm-hmm. I went out one time in Goldstone and took a look at that antenna. It's unbelievable how big it is. And when it moves, you can't hear it.
Oh, wow.
And my friend that was with me at the time, he looked at it and he says, gee, I'd like to get my motorcycle up there and ride it around in there.
It would be fun. But so just to make sure I understand you, so you're saying they're spending a ton of money on the data points, but they're not spending enough money to make full use of the data that they're getting, best use of it.
Well, no, I'm just talking generally. Mm-hmm. I have no idea what they're doing because I'm not involved. I haven't been involved at all in that mission. Mm-hmm. I'm just suspecting that they're not.
Okay.
Because if they were really analyzing it in the detail that I think it needed to be analyzed, somehow I think somebody would give me a telephone call and ask me a question about what I did on NEAR. Nobody has ever asked me a question about what I did on NEAR, ever, with regard to doing another mission.
Interesting.
And when Rosetta people over in Germany wanted to get some consult with JPL, they invited JPL people and kinetics people over there to talk about how do you navigate around a comet. Mm-hmm. They don't include me in that because they don't trust me that I might say something they don't like.
Right.
Well, when they came to JPL, I met with them and I told them exactly, and they liked what I told them so much that 6 months later. They sent some money over to have JPL come and work with them on something, like that. They wanted me. So what did they do? They send somebody else.
Hmm.
I don't know if you get the message I'm giving you, but what I used to say is that JPL just loves to pick up the number one incompetence that they can find and send them to help other people.
It seems that, managers have their plan and they don't like any voices that pipe up and threaten to alter the direction they want to go in.
Yeah, but I've worked enough that I understand that.
Yeah.
So what I want to do is that whenever they want to say something that's stupid, I want them to come to me and tell me. I mean, I'm talking about in public now, to NASA or wherever they're going to go. I'm working on the project full time. I'm doing all the work, but now we have to come and we have to talk to the customer. Mm-hmm. Well, they should, if they don't, at least come to me and discuss and tell me what they're going to say and let me comment on it. And then if I don't like what they say, I could tell them, okay, I'm not supporting you, or we could have it out privately. Mm-hmm. They don't even talk to me. They just go and do whatever they're going to do. They don't invite me to come along. I knew a guy. I'm talking to a guy who's from China, and he's done some really good work lately. Mm-hmm. And he's come up with a way of taking images and to help landing on Mars. Mm-hmm. And he got some kind of an award from JPL for doing this. He's really good at it. Mm-hmm. And now he's working on. He's come up with some way of processing an image and being able to take another image and then find things on one image that are also on the other image, so that you can navigate that way.
Right.
Cruise missile does this. The cruise missile images the ground, and then they have stored in their images, but it's very crude. But he came up with a new way of doing this, and Carnegie Mellon wants to go. There's some company at Carnegie Mellon wants to talk to him about this. We're getting a patent on it. But I told him, I said, I know what's going to happen. At JPL, I told him this before. I said, you got this award for doing that work. The next time there's a meeting discussing doing this kind of work, you will not be invited to the meeting. Because you know what's going on. They don't want you there.
Yeah. Well, so we're at 2 hours. I'm going to wrap it up here. It's been a really interesting conversation. I don't want to cut you off though. Did you want to add anything else, or do you want to save it for if we talk more about some of the work you did?
Well, I covered about half of what's on my sheet here.
Oh, okay. You have, okay.
Oh, I'm tired.
Yeah. It's a good talk, but okay. We can, if you have another half, we can, schedule something and talk about that.
Okay, we could talk about the purple plague on Mariner, the scan platform unlatch on Mariner, the sun shutter problem on Mariner, and then I go on Viking. I have the antenna gain at landing. Make sure you communicate and get a picture back when you land. I may have talked about these things before.
And, you might have touched on them.
And the famous, when we were working on Viking, the famous back of the hand compliments we get. That's a very good job you did there for somebody as stupid as you are. That kind of stuff. But we eventually got the managers and said, look, we don't want any more of those back of the hand compliments. I said, if you want to compliment, fine. Otherwise, keep your mouth shut.
All right. Yeah, we'll talk about that stuff next time then.
Yeah, I was just thinking I'm going to save these, because if I ever wanted to write a book, I got 90% of it. I don't think I have. In my whole life, I don't have anything else to talk about. That's all I've done my whole life.
Oh, it's plenty.
No, it isn't, if you think about it. Just think of how many times I could have played tennis, and I've done a lot of things.
Yeah, I guess so. I won't argue with you on that point.
Well, for that reason, most people don't do what I did. Yeah. I did it because I recognized what initially got me started was my great fear that if we don't beat the Russians, it's the end of the country. Mm-hmm. And that's what I believed. I believed it really strongly. I was really dedicated to doing whatever I could on the Minuteman program and on the submarines and all that, Mm-hmm. Then around 1971, when I was working on bombing with Minuteman missiles, I did a conclusion: this is all a bunch of BS. and from now on, I'm not going to worry about what the Russians are doing. So I went to work at JPL, and then I started worrying about whether or not we could get the space thing to work.
You found a new concern.
I've been motivated by thinking that what I was doing was important.
Hey,
and that's a big motivator.
Yeah.
And I never thought about it. I'm going to make a lot of money doing this, because I knew that's not going to happen. Because I knew that people who do things like I've done all my life, I know other people who have done these things. I could see them. They never get anything for it. But except the satisfaction of knowing you've done it.
Yeah.
And to me, that's worth more than anything else you can do. Yeah,
I'd say so.
You have to be lucky enough. I was lucky. I never thought I was not that good of a student in college. I had too many pressures on. My father died when I was a freshman, and I didn't think I was lucky to even finish getting a bachelor's degree. I had no hope of going on to graduate school. I had to get a job and work and make money.
Right.
And so my background is different than most people would experience today.
Yeah, definitely.
But when I look back on it, I don't credit myself with having accomplished anything. It's all the luck of being there at the right time and having the right people support me or help me.
Well, preparation.
In other words, I ran into a lot of people back early in my career. I'm trying to act today like they did with me. If I see a young guy, I try to help him, whatever it takes. Because I realized that was made such a big difference in my life. Yeah. Anyhow.
Okay, cool. So when do you think the next book is going to be completed? Any ideas?
Well, I have a date of June 30th.
Next year?
Yeah. Okay. And I got it. I had it written before. I got a rough draft of it, but I'm really going over it now and taking out some of the funny comments that I sometimes put in. Never put jokes in papers or books.
This is the end of part 2 of this 2-part interview. Thank you for listening. If you like this podcast, Technology in Space, please subscribe to it and rate it if you can. If you want more science, technology, and space history, please visit technologyinspace.com to sign up for my weekly newsletter to keep up with my latest posts. You can also find written interviews and my social media links there. Thanks for listening.